So So let's start. Today I didn't manage to prepare any printouts, sorry for that. So we'll just make an old school editorial without any paper. Let's start. What was the most popular problem? I think that was the problem 5. Problem 5 was about, it was about finding the number, making sure that all the numbers are getting divided into pairs, and there is nothing to discuss here, I think. So let me stand for. Also, there was an easy problem 2. Problem 2 was about gears. You were asked to find out in which directions will turn the leaf gears if you start turning some specific gear clockwise. Some of them are connected, some are not. There are no cycles on this picture, so everything will be able to rotate properly. And you were required to find out what's the directions of rotation of all the gears that have the degree of 1. Well, that was just an easy problem on DFS. You could have just run DFS, and from the first gear making when you make the transition, you invert the direction of rotation. So it was also really an easy problem. Almost everybody solved it, so nothing to discuss here. So problems 2 and 5 were really easy. Okay. Then there was a problem 6. Problem 6 was a bit trickier. There were lots of wrong submissions on problem 6. So let's discuss the solution of problem 6. There were almost no teams that submitted it from the first attempt correctly. There was only one team. So let's discuss it. The problem was about the following. You had a sequence of brackets of 4 kinds. And you had to check if this sequence may be transformed into a correct bracket sequence by swapping several, let's say, by permuting brackets in groups of adjacent contiguous brackets of same kind. Kind means closing or opening. So you had a string. It was divided into parts. Each part consists of opening or closing brackets. They alternate, obviously, and in each part you could permute the brackets arbitrarily, but not between the parts, and not like these and these. The question was if it was possible to perform such operations in order to transform our sequence into a correct bracket sequence. What was the solution? Well, let's proceed the groups of brackets from left to right. When passing through a group of brackets, if it is opening, let's put it into a stack. But into the stack we will store not the brackets themselves, but only a number of brackets of each kind, of each, let's say kind is closing or opening, and type is which exactly type, like the round bracket or the square bracket or whatever. So in the stack we store how many brackets of each opening brackets of each type we have. We'll store only the opening brackets in the stack. For example, we may have on the picture here, we first have this group, it's like, I don't know, 0, 1, 1, 1. Then sometimes we get the closing group, right? How does the closing group works? For example, suppose that we are processing the group of closing brackets. Here they are, and we have some stack. What is actually the stack? Stack represents all the brackets that are to the left and that are not matched yet. So we have several opening groups before that are not matched, and our closing group. What happens now? We need to match each closing bracket with some particular opening brackets from these ones. So how can we do that? The idea is that if the closing, there are if there are X closing brackets right here, then we will actually match those X brackets with the first X closing brackets in the resulting string if we follow from starting from here to the left, because we cannot match, let's say, this bracket with the one that is really like here, because it means that all unmatched brackets over here will be lost. So we are going to match this closing group with several full groups of brackets and one incomplete. How is it going to work? Well, what may go wrong? Let's say like that. For example, consider the following case. We have, like, let's say, one closing bracket here. We have like that. Then we have that. We have two, let's say, and we have the group of closing like that. So consider such a test. It consists of 5 brackets, or let's say 5 pairs of brackets, 3, how to say, curvy one, one square bracket, and one. Let's say we have also here something like. Okay, so what do we have here? We have several groups, like this. This, 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 this. Let's go from left to right. We will most probably match these two brackets together. So we will reorder, like, let's say, yeah, we will reorder like this. Then we have this one that is matches with this. Then we have like this and this that are two opening brackets, and then we have a not really good situation, because we have a group consisting of 3 brackets, one of which so let's write down like this, like 0 round brackets, one closing bracket and two curly brackets. We are going to match it with something. The closest, it's hard to draw them properly. The closest square bracket to the left is in the second group. Here we have a group, right? Here we have a group, here we have a group. Yeah, this is opening, this is closing, we already protest that. This is opening. These are closing. So we cannot match this closing group with those two brackets and one bracket from here, because here we have two round brackets, but we want, here is also this bracket. Here we have two round brackets, but we want to close one square bracket and one round bracket, meaning that we will not be able to match anything, to match this opening group completely with the new closing group. So once again, we have a picture like this. We are going to match all the brackets that are here with several previous groups completely and with one group partially. So the problem may arise that the opening group that is, for example, closest to our new closing group contains more brackets of some kind than this group. Like if it contains two opening square brackets and the closing group that we have right now contains lots of brackets but only one closing square bracket, it means that we cannot match everything here with here, so we'll have to skip some bracket here, so it will be completely lost and the string will not be a correct bracket sequence. So that's why we should check the following statement. The algorithm works like this. Well, we have several groups of opening brackets in our stack. We have some stack top right now. This is the top. It has, let's say, A, B, C, and D brackets of each type. And we just got a closing group that has like X, Y, Z, and T brackets of each kind. So we have to check the following thing. We try to match the new closing group with the topmost opening group. What does it mean match? From each component we subtract the minimum of, for example, here we subtract minimum of X and A from both A and X. We subtract minimum of Y and B from B and Y. So after that we have three options. It may be that closing group will be looking like 0, 0, 0, and the top opening group will be like something. In this case, it means that we matched everything that we have here with something previously, and we just complete working with this closing group afterwards. It may be possible that the closing group looks like something, and the topmost opening group looks like 0, 0, 0, 0. That means that we have, for example, this case, we have three closing square brackets over here. We match all the square brackets here with brackets here. All the brackets here are matched, so we just remove the topmost group from the stack. In this case, we just pop and continue the process. And the last case is that both closing group has something non-zero and the topmost opening group has something that is not zero but on different positions. Otherwise we would have just reduced both of them. So in this case it means that we have a situation like I described, like here. Here we have 1, 1, 2, let's say 1, 1, 2, 0, and here, one second, Yeah, and here we have the opening group that contains 1120, let's say 2000. It means that we cannot match everything that happens here with what happens here, because here we'll have unmatched round bracket, and here we will have unmatched lots of brackets, like 2 curly one and 1 square one. So this means that the answer is no. After performing all of this, we should check that the stack is empty. It would mean that we have successfully matched everything we had. So, are there questions regarding this problem? The implementation was not really hard. Yeah.
Think about the case with the empty seconds.
With empty
Seconds. It was correct.
with the test with empty sequence.
Yes.
I think there was no such test. I think that constraints. Let's say you could ask a clarification, and I would have told you that there was no such case. And even if it was the problem with an empty case, I think the empty sequence can be considered a correct bracket sequence according to the formal definition without any problems. So it's just like you could have spent 2 attempts on finding that out. Any other problem? Any other questions? Yeah.
The time limit for this problem was a little bit tight.
Tight?
Because our algorithm was linear and we used to know SQL structures, only arrays, and SQL and FastIO, and it passed, but really close to the time limit.
Seriously? I think that sounds not realistic, because you see there were like 2 seconds for a solution that performs like a million operations multiplied by maybe like 4 or 8 or 12. So I think it should pass without any problems. You used FastIO for that, and did you use also 1 second, and which compiler did you use? So which compiler did you use? C++14. Well, I should have told you, on Codeforces, C++14 works pretty strange. It sometimes has a really slow I/O that is even built on the top of low-level functions. Even if you use your own I/O, it may sometimes hang on Codeforces. When Mike Mirzayanov comes here, you may ask him why so. But now I suggest you not to use C++14 and use C++11. Well, just try to send your submission in C++11, and if it still works like quite long, then show me. It sounds pretty strange. Well, I can tell you that there were solutions that passed in, give me a second, I think in a negligible time. That was the problem 6. There were solutions that work in 300 milliseconds, so I think that's just an issue. Oh, there was also a solution in C++14 that works like 200 milliseconds. So I think the reason is somewhere in your solution. If you want, we can just look on it after the editorial. Are there any other questions for this problem? Yeah. Please be quiet, I don't hear. Yeah.
I did this problem and submitted it in C++11.
Yeah.
And I got a time limit. And then when I changed it to C++14, it passed.
Well, whatever. There was a strange fact that found out by user Halyavin on Codeforces that actually the C-in and C-out work faster in C++14 there, because well, the difference is that in C++14 they tried to implement the library that is in Linux. Well, if you use Linux, there is a standard library, the runtime library like libc under Windows they have used previously the Microsoft Visual C runtime library, and they tried in 14th version in the MinGW GCC. They tried to renovate something there, to port libc under Windows, and they really didn't succeed in it. So it works pretty strange. I try not to use C++ 14 because it may sometimes result in a pretty strange time limit exceeded. So let's move to the next problem. Next problem was the problem. Which problem was the next problem? 4? No, not the problem 4. The problem I think 7. Problem 7. Oh, problem 7 was a nice problem. It was solved by 15 teams. Wow. Or not. So problem 7 was about the following. Problem 7 was kind of a classic problem from a theory of, let's say, from the area that studies codes, studies ciphers, and so on. So you had a code that consisted of, let's say, each letter of the input alphabet is mapped into a string that corresponds to each letter. Then all the letters, all the representations of the letters being concatenated, and you are interested if this code is uniquely decodable, decipherable. So that means that you are interested if there exists a sequence like AC1, AC2, and so on, and ACK, and another sequence AC1, AC2, and so on, ACL, that are represented with the same, well, whose concatenations are the same. So this one equals to this one. And those sequences are different because, of course, if you take the same sequence twice, they will be equal, but that's not interesting to us. So we have to check if that is possible. How to check that? Well, let's see how the picture can look like. This is the top sequence. It is divided like in some parts. And here is the bottom sequence, the second one. It is also divided in some parts, but maybe with different bounds. Maybe in different number of parts. So let's say like this. So how can we deal with this problem? Let's try to figure out, let's try to represent the way of creating such a collision as finding a path in some graph. For example, what happens when we stop somewhere? For example, let's stop over here. If we stop over here, the picture looks like the following. We already have some word that we already opened, so we have some suffix that we have to follow. So we know the prefix of exactly the same length in the second word. It should be the same. And it means that in the second sequence, the words here are restricted to those that have exactly this prefix. It means that not every word we can put over here. Actually, by knowing what is the suffix of the word here, we know that word here may be one of several of those who have this prefix. Okay, let's try to say that we have picked one of them. We picked some word, then we move to the next point, and then we already know something about here. So we know how this word should look like, and so on. Let's describe that more formally. We will build our two sequences from left to right using the following algorithm. Let's say we start with both words being empty. So this is the empty word 1 and this is the empty word 2. At any moment, this is beginning, start. At any moment the picture will be like the following. We will have two sequences partially built, having possibly the different lengths. They are already matching by the length of their, let's say, the minimum of their lengths. So in this case, let's say the first one is always not shorter than the second one. They are matching. That means that the prefix of length, the length of j, what does it mean ij, the length of the first one, a, is larger than b. That's what I want to say. So they match by the length of b. It means that up to this place they are similar. And we are going to add one more word. We are not interested in adding words to the longest sequence. Let's always add words to the shortest one of them. If we add a word here, what may happen? There are two possibilities. We may either add a short word, like let's say word of about this, like this length. Let's also remember which word is the last in the longest word. So let's remember the index of the word that is the last in the longest sequence, and remember, yes, its index and its length that we have already used. Let's call this L. So okay, we now want to add one more word to the shorter sequence. We add it, and the first possibility is that it is short enough. Then we may add not any single word, but only those that match with the substring of the last word here with the corresponding bound. So if the word, let's say the word J, is completely matching with the part of word I that starts from the position L, if they match, then we may move from the state IL to the state I, L plus the length of J. This is one possibility. And another possibility is that we add a new word that is long enough to cover the word J. So we had picture like this. This is the word, the word I. This is the word I. We have already used L of its characters, and we are adding new J, such that the remaining suffix of I is similar to the prefix of J. So if this equals to this, we are moving to the new state, but this new state will be not like I something. In this state, this will be the longer word. So we are moving to, let's write here, to from IL to J, and the length of the already used part here is something like len of I minus L. So here are the two transitions that we may use. We start from the state that does not look like this. We start from the state in which both strings are of the equal length and they are all empty. So let's tell that we have an extra start state. For example, you may tell that the start state is like 0, 0, whatever. And you are interested in getting to the state when you have sequences of words that have exactly the same length, because we guarantee that they match up to the length of the minimum of their lengths. That means that we'll have two sequences that match, and that are, let's think about how to make them completely different. Actually, in order to make them completely different, the only thing you have to guarantee is that you never add, let's say, exactly the same parts together. So you should not have a situation like this, and with all those words being the same. But you will never do that. You should, if you choose the transitions from the start state properly, just make sure, well, if I implemented that, I would call that the start state is not like this, but the start state are all states like, let's say, IL, I length I0, yeah, these are all start states. Meaning that I have fixed that one of the words here will be I, we use 0 characters of it, and the other word will be whatever we want. So, and what we need to find out is that if it's possible, by using transitions like this, get to the state in which it is once again something like I0. So actually you have a graph on such with such states as a vertices that you are interested in finding a cycle in this graph. So build the graph. The graph consists of how many states? With each I we have exactly length of I states. There was like 50,000 characters in total at all. It means that there is 50,000 states, so vertices in that graph, and there is at most n transitions from each state. How to understand if we are allowed to perform a transition from some certain state? Well, you may do that using any way of comparison strings that you want. You may use that if you very like suffix structures, you may do that using a suffix array, I think. If you are not that kind of person, just use hashes. They work pretty well here. Just compare the corresponding substrings using the hashes. So that's the solution. It works in n multiplied by the total length running time. So are there any questions? Yeah.
Is it possible to solve it with modifying
Echokarasic? I'm not sure, because you are interested. Let me think.
Like
Echokarasic, you want to check if the new string matches some string over here. You have to check if it matches. I don't think, because you see, Echokarasic is an automaton, and usually you work with automatons by actually submitting all the characters that you have as an input for those automaton, by actually visiting all the vertices on that path. So I don't see a way how to perform those transitions fast. Yes, you actually may have done something like that. You store Echokarasic of all symbols, then when just having the J, you submit it to the automaton, and you check that there exists a transition that is on the path of from the root to the leaf I. But it's some kind of overkill, because you could just without building a heuristic, you could have just compared all those characters one to one. And we do not want to compare each character within each character in this solution, because it will multiply the overall complexity by the length of the string one more time, and it will be definitely slow. So I don't think that it is possible to use a heuristic somehow here, because in this solution you have to perform transitions pretty fast. All your transitions are of form some given string, and it is hard to perform like fast transitions for some generic strings in automatons. I don't think so. Something like that. Are there any questions? No questions? Okay. No questions, no questions. Yeah.
Please explain again that part of reverse graph. What is reverse of graph?
Okay, so once again, when you consider the process of building such a collision pair, what's that? When you consider the process of building such pair, let's move from left to right. At each moment of time, there will be one longer string and one shorter. Let's say that this situation is called a state IL. That means that in a longer string, in a longer sequence, the last string is a string I, and we have used the prefix of length L of it. Okay, what are the allowed states? The allowed states are like the following. Let's say that we allow only states of form IL where L is not equal to 0. Let's say like this. It may be easier to understand. So we allow only states when this actually implies that we allow only sequences that are not equal to each other, and this will be the states in our graph. Then let's say that we have here one more situation, let's say terminal situation. That is when we move from state IL to the finish. What does it mean, finish? It is one more transition when you add exactly the string, you are needed to have the sequences be of the same length. So this is the finish state. So you have several states, each of which is like IL with L not equal to 0, and you have one extra state that is called finish state. You are interested in getting from some initial states to the finish state. What are initial states? Initial states are like, let's say, let's say that you start from a situation like the first string has some I here, and with the IL with L not equal to 0. There was some not really cool place here. Okay, let's say that L is allowed to be 0, whatever. We'll just see if this works. So let's say that all the start states are exactly the states of form IL where L equals to 0. These states correspond to the situation when we have two strings. We already decided what will be the first word, the first string inside the first sequence. It will be the string I, and we want to start growing in the situation growing from like this. Okay, these are the start states, and we are interested in getting into a finish state. But so those states will be the vertices of our graph, and the edges will be the transitions between states that are described by these rules. The transition of the first kind is when we add a short enough string, it matches everything here in a long string, and we just move to the state with the same I, but with longer L plus length of J. The second kind of transitions is when we add a long string and we move to J and len of I minus L. And the third kind is when we add exactly a string that is exactly length of I minus L long, and that matches the suffix of long string, of the last string that we have here, and it means that we are getting to the state when two sequences are actually equal. Why did I want to say that L was not equal to 0? Well, there is a small issue is that if you run your solution exactly like I described, then you will most probably at the first step you will try to add a string I over here, and it will match the string I, and you will immediately get to the finished state. It means that you should restrict yourself from performing transitions that are trivial. Trivial transitions are of form IL by adding a word I. So let's say this means that we add the word J. Let's denote this transition with an index of J. So the states like from I0 using I to the finish, such transitions are not allowed because you don't want a trivial collision of form II. This is not interesting at all. So okay, consider the graph on all states IL and an extra state for finish. Run the DFS starting from all IL with L equal to 0, and if there is a way to reach the finish state, let's say forget about cycle, if there is a way to reach the finish state, you're done. You have found the collision, and the answer is yes. So, are there any questions? Okay, this is the more detailed version of how to implement it. So the next problem was probably problem 8. Oh, problem 8 was kind of tricky. Problem 8 was the following. You had a set of stacks. Each stacks contained colored and let's say gray colored and how they were called, colored and black-white photos. Each stack contained several photos, and you were interested in a question: if it is possible to put all those photos in a box. Those are stacks, and you have an empty box. Let's call box. You have to put all of them over here, meaning that you using the following operations. You get the several topmost photos from some stack. You just take them and put onto another stack, or you put them into box. Also, you cannot take the photos from the box. When put there, the photos just stand there forever. What is the minimum number of operations you have to perform like that in order to put all the photos in the box in the correct order? Okay, the statement used pretty inconvenient way of writing the stacks. It was writing them from top to bottom. So let me consider another way of writing it. So this is the bottom. Let's say BW, BW and C, BW. Yeah. So stacks grow over there. This is the top. What are we going to do? What are we going to do? Let's look on which stacks we possibly may ever get to the box. First of all, let's do the following operation. Consider all groups of adjacent photos of the same kind. It's pretty easy to see that it is never profitable, it is never a good idea to split them, because instead of splitting them, we may have considered them as a single large photo and just to do everything we wanted with a single large photo. This is not real, this is not splitting them does not allow us to do anything more than we can do without splitting them. Okay, so now we have situation when each stack is described actually by its length and the topmost photo. So which kind of parts of stacks we may ever put to the box? Well, it's easy to see that the box at the end will contain like the sequence of photos that first several of them are black-white and last several of them are colored. It means that we will always put parts consisting of the same kind of photos, except for maybe one part that will contain the black and white photos and the color photos above them. So there is one, let's say, critical part, and all of the remaining parts are actually the single color parts. It means that we'll first put parts. By the word part, I mean the part of the stack that we just get and put somewhere. So we'll put like single color parts, single color black parts. After that, we'll put one maybe part consisting the black, white, and the color above, and several single colored parts. So yeah, this is the problem A. Okay, how can we use that? Note that the answer, this proves that the answer is no less than the sum of lengths of all stacks minus 1. Length means the length after we joined all the consecutive photos of the same kind together. Why so? Well, because look on this following, on the following number. This is exactly, well, let's say, because after we perform an operation, this thing decreases by no more than 1. I don't like the way how I described it. Let's say the sum of lengths, the sum of lengths. Yeah, okay, let's say, let's write it like, not like the sum of lengths, sum of, let's say that, okay, number of groups of different, number of groups of adjacent photos. Okay, let's not, it is not really necessary to join them together. You may either join or not. The solution will deal with the groups of adjacent photos of same kind, because after you perform an operation, after you get, for example, this here, you will once again get a group of consecutive photos of same kind. So let's say that the number of groups by each operation decreases by no more than 1. Actually, it transforms to the number of groups plus or minus 1, or maybe the same. Why so? Well, because consider two stacks, or the stack and the box that you have affected. You have a stack You have just taken its top part and you have put it somewhere else. What happens next? If you took exactly the number, like you have splitted it exactly between the photos of different colors, then here you'll have number of groups being decreased by some d, and here there are two possibilities. If the bottommost photo is in this part you have taken is different from the topmost photo in this stack, then you will just increase number of groups here by d. Or if those colors match, we'll actually join the group here and the group here together, and you will also have -1 here. So in total the number of groups will be changed by 0 or by -1. And the other case is when you have splitted the original stack between two photos of the same color. We already discussed that it is not a good idea. We do not need to do that. But still, let's consider this case. In this case, you will have here like +1 possibly, because when splitting a group into two parts, you will actually create two new groups. So here you have maybe +1, here you have maybe -1. In together, like in sum, this means that the overall number of groups, this is the total. So the sum changes by the sum +-1. That means that if you had, let's say, if you had G groups originally, it means that you cannot reach the answer, you cannot put all of them into your box in less than how many terms? Originally you had G groups, and by the end you have like 1 or 2 groups, right? One group corresponds to the case when all the photos that you have here, they have actually the same color. Yeah, this is the original number of groups, this is the final number of groups. It means that you may not finish faster than in G-2, faster than in, let's say, this proves that you have to spend like at least G-2 turns. But let's see, where do we get one extra turn? But actually its answer is no less than G-1, I'm pretty sure about that. Yeah, actually you have to spend one more turn in putting everything in the box. It means that, you see what happens? This C, BV, BW. Okay. You have to put everything over there. You have BWC getting over there. And on each turn, the number of groups reduces by 1. Reduces by 1, by 1, by 1, by 1. You have to join those two groups together. Like, let's say, here is the case. BW here, and the empty box over here. So we have to spend one more turn. BW, at least the number of groups over here, -1. -1. Why do you have G minus? Oh, everything is correct. So well, okay. So once again, yeah, let's do the following. Let's say that we have an extra. Let's imagine that we already have one more extra black and white photo at the bottom of the box. It will, well, or even we do not need that. Wait. So, once again. Okay, let's write our solution like the following. Yeah, we will have an extra added by us black and white photo at the bottom. We want to get everything to the box. Let's consider two cases. First of all, the first case is when all photos are of the same color. Well, let's say are all of the same color type. It means they are all either colored or black and white. In this case, it's obvious that we have to spend exactly the n turns in order to get everything in the box, where n is the number of non-empty piles. There were no empty piles in the input, so it's exactly the n you had. Okay, the other case is when you have both black and white and colored photos. In this case, what do you have originally? Originally, you have how many groups? If you do what I told, if you like put an extra black and white photo added by you over here. This is like imaginary black and white photo. In this case, originally, you have G+1 groups, where G is the number of groups in the input, and you have to transform it to exactly two groups, to the two groups that are like the group of black and white photos and the group of colored photos that we have here. This means that we have to perform at least G-1 turns. Okay, now it works. So we have to perform at least G-1 turns, and we may perform G-1 turns only if at some moment we do what? Yes, in order to perform at least G-1 turns, it means that at some moment we have to put the part that I have shown you over on this picture, the part that consists of black and white photos and colored photos. Let's call such a part a two-part. Bad words. Let's say I don't know, a nice part. So if we have a nice part, then we are able to do that in G-1 turns. And if we do not have a nice part, we'll have to do it in exactly G turns, because we will actually take each of those parts and move them to the box separately, and we have G parts over here. So once again, this is the lower bound for the number of turns. Actually, the answer is always G-1 or G. We will prove that by showing an algorithm. And G-1 happens only when you have, only when you are able to put a nice part in a box. The nice part is the part that both contains colored and black and white photos. Why so? Because, okay, let's try to come up with an algorithm. Or it may be impossible in some cases. Yes. Okay, so suppose that the first case we need to consider is when n is greater or equal to 2. What does it mean? You have at least two stacks. You have a box. And you want to put everything to the box. Wait, 1, 2, 3, and the box. Let's use the following algorithm. Let's try to put, first of all, let's try to put the, let's say, if we have somewhere at the top the black and white photos, let's just move them to the box. After we do that, we'll have n stacks, each of which is either empty or contains a colored photo at the top. Let's call one of the stacks that contain colored photos the intermediate, the temporary box. This stack will be the temporary box. What's the idea of being temporary box? Now we have a situation like here we have several black and white photos. All these parts have gone. We have many stacks with the colored photos on the top, and now we will do the following. We will take the colored parts of all stacks except the temporary box and put them into this temporary box, and when we get the black and white part, we'll put them into the actual box. It means that until all the stacks except the box, all stacks except the temporary box are not empty, well, until they are empty, we do the following. If we have a colored part, we put it into the temporary box, and if we have a black and white part, we put it into the box. This will result in that at the end we'll have like the one large stack consisting of colored photos in the temporary box and another large stack consisting of black and white photos in the box. After that, we just put all the colored photos above the black and white photos, and we are done. This works exactly in G turns, because on each step we just take on all steps except the last one step, we will join two groups together. Each time we put a black-white photo here, we join this black-white group with the previous one, and each time we put a colored photo here, we also join it. So on all steps except the final one, we'll reduce G by 1 each step. And on the last turn, we have not actually reduced G by anything, we just move the colored group to the black and white group. So we already know, in case of n greater or equal to 2, that the answer may be G. But let's see when it is possible to get G minus 1. What is the unoptimal place in our algorithm? The unoptimal place is when we got all our colored photos and put them above the black and white photos, and we didn't actually join anything here. Sorry, I think I'm wrong.
If you want to have one stack and you have empty stack, you may have to change a quality to the empty.
Okay. Once looks like I'm wrong here. But is it true that the answer is always G or G minus 1?
Yeah.
It's true. So, okay, so the situation is when we have C black and white, C black and white, and we have like like the empty stack here. Okay, we do not have empty stacks, but whatever. And we want to put them into the box. And the question is how to do that quickly. We want the nice part that we have here. Okay, nice part. This or this? The right part. Okay, so we just want to use this. Okay, we put like C here, BW here. Then CBW here and C back here. Okay, but what happens? So it was 1 BW here, 2, 3. It still works in G terms. I thought it was.
Why second bit is not empty? If you do not start com second names, you would join a C union the groups.
So if I
At the starting, not period set. Not starting set.
not start. Sorry, I didn't get. Can you please, for example, go to the yeah?
Do you have two stacks and you one is empty or not?
Yes, we are discussing this case.
Getting the input one stack empty.
Yes, we cannot get it. Okay, let's consider the different case when, let's say we have C and BW here.
That case is
In this case, I think we should be able to deal with it in 5 turns, right? And how can we do that? Well, I just kind of messed somewhere.
you can put C, B, and
Only C and B?
no,
Or
C and B.
this C and B. This C and B.
No, C over C. C over C.
Ah, C over C.
Yeah.
Okay.
And then black and white over the box.
Okay, black and white over box. C over C. Once again, black and white over box.
And then stack 0.
Okay, and okay, that worked. But if we, let's say another case, if we had like also C, BW, C, BW here,
Same case. No, you have to put C, B, C over the C.
C over the C, then BW over here, I think in this case we want to deal with it in 7 turns, right? So C, B, C over C, okay.
B over
B in the box, then
C over C.
C over C on different C. Oh, okay. Ah, okay, I get it. So, yeah, instead of choosing the, yeah, okay. Let's say that we will not have a temporary box because, yeah, okay. We'll have a situation like this. We'll have some box that contains a large pile of current, the current pile containing all the colored photos we had to put somewhere. So we will be doing it like the following. We will be keeping the, like, here we have our picture. There will be a pile of red photos on top of some stack, of some of the stacks. It will grow, right? It will be like on each turn. If we have a B photo, we will put a black and white. We will put it to the box, and if we have a colored photo, instead of putting it to this like into this special pile, we will put the special pile onto it. It will still result in joining 2 groups together, but it will allow us to finish in a situation when we have like lots of colored photos in some box and lots of black photos in a box. Because, well, the only thing that we're afraid of is that we will get the situation like we have a large pile, but beneath somewhere there will be a black and W photo that we have to extract from here and put over here. So this is the bad situation, but we will actually do not get into it, because if we see that there is like C here and C here, and if let's say there is nothing below this C, then we will put this pile over here. Otherwise, if this C is also on the ground without any B and Y here, we will put the smaller C's over here. So by choosing the correct direction of join, we can actually like save, make all the colored photos be stacked above the ground, above the bottom of the stack by the end. And this will be the algorithm that works in exactly G. We do not used a nice part anywhere. And here the nice part appears. I think the nice part is like what? The nice part is, well, let's say that if we have a nice part anywhere, the nice part is like BW and C. Then we have to, at some moment, oh no, not BW, C, vice versa, C, BW. At some moment, we have to save it. Okay, let's see. Okay, let's save the time first of all. I think let's do the following. Let's tell that it is possible to prove. Well, when I solved this problem back then, like 3 years ago, I've definitely proved that. I'm sure about that. So after all, let's say that it is correct that we will spend like G turns. If we have no nice part, we already proven that it's possible to do to do it exactly in G turns. And if we have a nice part, it's not really hard to see that at some moment of time it is possible to put exactly when we have the last black and white. Oh, whatever. It is possible at some moment of time to use it and to put it actually in the box. Let's say that it is possible to prove that. And okay, this results in a solution for the case when n is greater or equal to 2. And in the case when n equals to 1, there is a special situation. You should have found that if we have like at least I think 5, right? At least 5 groups in a single stack. So let's return back here. This is what we have: G or G minus 1. And in this case, if we have at least 5 groups, then the answer is no, because if we have 5 groups, it looks like BW colored, BW colored, BW, and it looks like C, BW, C, BW, C, and whatever turn we take at the beginning. For example, here.
If you have 4 groups, the answer is no when the case is C, B, C.
Yes, that's correct. I just started from telling that for G greater or equal to 5, it's definitely no. Let's stop on it. Why so? Because if the answer is, if the picture is like this, then we have to first extract BW, then we have to extract CBW, and then we'll still have BW here. It won't work. And same for here. We cannot put anything into the box because we have BW below C. Also, when case is G equals to 4 and it is like B, so which case we cannot work. The case when C is on the top, in this case it is no, because we cannot put anything to the bottom of the box. It will result in that we have BW above C. So, and the last case is, well, else. The answer is what? I think the answer is still G minus 1. Let's say if we always have to spend at least 1, so the answer is, I think, G minus 1. Okay, G or G minus 1, depending on if we have a nice part. Yeah.
Which example G of 4 is possible?
In which case G equals to 4 is possible? I think in this case, in this case is possible. First we put BW, then we put CBW, and then we put C. And it works, right? Okay. Okay, sorry for that problem. I should have prepared it better. So, yeah, this is the correct solution. At least I hope so. If there are any questions, I'll try to answer them. Are there any questions? I think those who have solved this problem just tried to verify what I was talking, and those who didn't solve didn't get anything. Sorry for that. So, well, that was the algorithm. Just get the idea that the answer is always g or g minus 1 and try to figure out how exactly it is possible to do that. So it's 6th, 7th, 8th problems. Okay, the next problem was probably the problem that was the problem 8, and now we have several hard problems. Problem 5. Yeah, let's talk. No, problem 5 is not hard. Problem 3. Oh, the problem 3 was pretty nice to implement. You had to parse a lot of things. You had to parse the file tree, and then you had to print it in a paged mode using the least number of pages by compacting minimizing some of the directories, and by writing, instead of the content of some directory on one page, you just printed name and the sign that is minimized, and on some other page you print the whole content of that directory. So how to solve that problem? First of all, parse all the input. Parsing input is really hard here, but still it is possible. Parse the input and build the tree of the file system. How does this tree look like? It contains several vertices. All the leaves are, let's say all the vertices are either files or directories. I think there were empty directories. Yes, I think, yeah, we have, or not, minus docs, minus programs. Could we have the empty directory? No? The names. Okay, so we do not have empty directories. This means that the leaves are also the files. These are files. And the vertices, the internal vertices, are nodes. So what do we do then? After that, the procedure of minimizing some directory, printing it separately, actually results in what? Actually, for example, if we decide to minimize this directory, it means that we will actually get this subtree out of the tree and print it separately and deal with it separately. And we will deal with well, in the remaining tree, in the top part of the tree, we'll have only leaf instead of this whole directory. So the problem was exactly about the following. You should extract as small number of subtrees as possible, such that each subtree that you extract contains at most like W lines. W lines means it contains at most W vertices. So what did you need to do here? After you parsed all the input, it was pretty hard, but still it was possible. You had to solve a graph problem, actually. You had an unordered tree, and you had to extract several parts, such that each part, let's say it contains no more than W minus 1 edges. It's more even easier to look on edges rather than on vertices. So you do that. How can this be done? It may be done using dynamic programming, but it will be really slow because you will have to keep many states. So this actually can be done using some greedy algorithm of the following kind. You start from the tree. from the whole tree, do a DFS, a depth first search. When you see, for example, so the overall idea is to do a DFS and perform the cuts, cut out the parts only when it is really necessary to. So you perform a DFS. For example, this subtree and this subtree are both okay. They still fit in the limit of W vertices or W minus 1 edges. But this subtree, this one, is larger than needed. It means that we have to split out several subtrees out, let's say, to minimize several children of this vertex. This may be done actually greedily. We should do the following. We should, I think, sort all the subtrees here by the size, and then to minimize those of them who have the largest size in order of decreasing size. We do that until the size of this subtree will not become smaller than W vertices. And then we continue the process. But I'm not sure. Is that correct? Anybody who solved this problem, did you do the same? There were 5 teams who solved this problem, I think. Anybody? You're not going to help me, right? So I think this is a correct greedy algorithm. Let's try to prove it. Why this may be correct? Because let's do the following. Yeah, okay. Let's do the following. Actually, this algorithm, it has the following property. Consider some vertex. I claim that this algorithm extracts as little pages as possible from each subtree if you have fixed vertex V, then it extracts as little pages as possible, and among all those possibilities, the remaining size of what will be attached to a vertex V is as small as possible. So it minimizes the number of pages and the remaining size. Let's say lexicographically. It first minimizes the number of pages and number of remaining vertices. Why so? Why wouldn't it be more, let's say, more efficient to spend more pages somewhere here, but get the remaining size here smaller? Because it wouldn't be more efficient, because let's say you have 2 options. The first one extracted 2 pages from here and left you with 10 vertices. The other one extracted 1 page here and left you with like 5 vertices. The question is why, the question that arises is why it is okay to minimize first the number of pages and then the number of remaining vertices in this component. Because maybe it is more efficient to have number of pages a bit larger, but the number of remaining pages smaller. Maybe it is more efficient to pass it like upwards. I claim that it is not more efficient because if we have, let's say, that if we have like 2 options, like leaving. How to prove that? The proofs were not. I didn't like the proofs at any moment of my time. I always hated proving anything. Always proving greedy is always very hard. So, okay. Suppose there is another way that we can do that. That leaves us with 3 pages, but like 4 remaining vertices. May it be more efficient? I think not. I think not, because if we start doing the same over here, then the decrease of the remaining vertices from 10 to 4, let's say that W is equal to 12. Yeah, the decrease of the number of remaining vertices is smaller than W. It means that it will result on the top part of our algorithm on the top level, it will result in that we can spend at most one page less than previously. So we have like one page less here, but one page more here, and it somehow compensates. This is not really a strict proof, but I think it may be done strictly if we just suppose that there is another option that is better, that uses p plus x pages, but some smaller rem minus y number of vertices. And I think it is possible to prove that we will have to, we cannot like deal with smaller than what we had above -1 number of pages. So this is not really profitable at all. So whatever. The solution, it looks like the DFS procedure that returns you the pair of two numbers. Number of pages you currently have and number of remaining vertices. Just in each vertex V, just call it, run the DFS of all the children of V, and then look what they return to you, look at the total number of vertices. If it is larger than W, then sort all the trees and cut the largest of them until you're working good, until the number of pages is W. Number of vertices no more than W. Okay. Are there any questions? Yeah. More detailed proof. It is an interesting question. There is no like nothing like an editorial. Let me. Well, I'm sorry. I didn't find the time to prepare the proofs properly yesterday. I was kind of busy. So I think that I'm going to do the following. I think that after our lecture, after all the stuff we have today, I'll try to prove it more formally, and I'll try to like at least write it somewhere. I think, well, I don't think that I'll come up with anything more like formal than this. So let's just move to the next problem. Or any other questions regarding how to implement it or something like that? Yeah. Is it possible to not close the folder but close something of its descendants, like the more inner folders?
Yes, like we have the root folder and then some subfolder. Then we open it, but close some of the subfolder.
Like the, I don't know, the -a, -b, but closed C, right? Yes, it was possible. It was not prohibited by the statement anywhere. So this corresponds to the case when we, for example, have such a picture, and you may have at most 3 vertices per page, and then you have to, this is A, B, C, D, E, this is file A, B, C, and C, D, E. I think this corresponds to this case plus this, and to such a division of the tree. It was possible. I think there was also one team that asked me a question about that, and I answered that it was possible, and actually it is possible in the test. So. Sorry, once again? No, not all the descendants. You see, process that I described works like the following. The DFS of here returns to here the information like 0, 1. It means that there is one vertex here, and 0 pages have already spent here. Okay, on this level, we look on all those pairs. We just sum them up component-wise, and add one vertex that corresponds to this vertex. So it will be like 0, 2. On this level, it will be 0, 3, and on this level, we'll get 0, 4, but the W is 3. So we will have to cut out at least one of, well, yeah, we will have to cut out this subtree. So you're correct in terms that the my procedure, it closes only the directories that are descendants of the current vertex. But the current vertex may not be the root of the whole file system. Actually, I close this vertex when I stand over here, so it will, I replace 0, 4 to like 1, 1, 2, and I pass here, it gets 1, 3. And overall, it looks like I have closed this directory, and it is the innermost. It is not the exact sun. Did I answer your question? Okay. Any other questions? Okay. So, do 3. Okay, let's talk about problems 9 and 10. 9 and 10. Yeah, the problem 10 was really an interesting problem. This was the problem, which problem this was? This was the problem 3. Okay, the problem 10 was about a planar graph, about the set of vertices and edges that are drawn on the plane, and you were asked the following question. We want to choose some guarded area here such that the ratio of the number of guards divided by the area is as small as possible. And you had restrictions like if you decide to choose to protect, let's say, if you decide to protect a territory like this, you have to protect some polygon, some non-intersecting polygon, and you do not have to protect all the watchtowers, for example. Something may left outside, some watchtowers may be inside. That's completely okay. So you have to spend the number of watchmen, of guards that is equal to the sum of numbers that are written on the edges plus the numbers that are written in the vertices of the polygon that you have chosen. You had to find like this. This was the problem 10. Okay, this problem solves with a trick that really, please remember it. It is really common and it is really easy. The trick is the following. When you have to minimize some ratio, what do you have to do? What do you have to perform? Which operation? I claim that it is really convenient to do a binary search to try to find if it is possible to find a polygon with number of guards divided by area smaller or equal to some alpha, and then do a binary search over all alphas. It's pretty easy to see that function is monotonic. For alpha like negative alphas, it is possible. It is not possible to choose some polygon. For the alphas that are really large, it is possible. At some moment there is a breakpoint, and you have to find it using the binary search. It will be exactly the minimum possible value of this fraction that you can get. And why does someone want to use the binary search here? Because the fractions usually work like this. If the fraction is not greater than alpha, then the number of guards is not greater than, let's say, alpha s, right? Then what is the number of guards? Let's say that we will consider the oriented polygon in some order. We will say that the G of the edge, it contains also all the guards that are on the endpoint of this edge. So we will say that we will not have GV, but we will add the GV to GE, where E is the oriented edge between U and V. So we have GE, then this is the sum of GE over all E belonging to our polygon, sum of GE. And this is actually what? This is actually alpha multiplied by the sum over all edges of our polygon of what? Well, you know how to calculate area using the edges of a polygon, right? This is alpha multiplied by sum over all edges of vector product of PU multiplied by PV. Yeah? I think yes. And everything is divided by 2. So this is the equivalent statement. E equal to like UV. And let's bring everything that is here over here. Alpha GE minus alpha divided by 2 PU PV by over all edges of the path P, of the polygon P. It is smaller or equal to 0. Okay, notice that this thing, it depends only on the edge E, on its endpoints U and V. So let's denote this as WE. And what do we get here? We get a standard problem in a graph. We want to find a cycle of a negative weight. And that's all, the solution. So this problem was actually really easy to implement. There is one question that I don't know how to answer right now. That's the bad day for me to run an editorial. But it was the question actually about minimizing that ratio, right? We wanted to minimize that ratio. So the only question that I have here is what happens when we get this like negative. We may choose the wrong direction for the polygon that leads in a negative area. Does that ruin anything actually? Well, I think not, because if we choose the negative, if we choose the negative, the wrong order here, then this inequality cannot hold because this will be negative and this is positive. Yeah, so exactly. Actually, we have to, the only thing that we have to check is that there exists a cycle P such that sum of weights of all the edges on this cycle P is smaller or equal to 0. So that is a negative cycle detection problem. Is the solution clear? I suggest you to remember the idea with the binary search tree. It is really common, and sometimes it allows you to transform problems into a really different ones. Sometimes it's possible to transform a problem to some max flow problem using this trick. Okay, so that was the solution of problem 10. Let's talk about problem 9. Problem 9 was stereometry. Problem 9 was stereometry, and it was not really hard. It was completely possible to write down that stereometry. So what did you have here? You had the following picture. You had a big round spot on the planet. Wow. You had a picture like this. Okay, and you had to find out the area that is visible to the spaceship that is far, far away from somewhere, looking in some direction. Well, let's imagine that we are on that spaceship and we are looking on that planet and that spot. So let's say that we are looking from here to that picture, and we want to find out which part of the area of the surface the spot takes, so the ratio of this part to the whole circle. Well, how can we do that? Actually, what does the spot of which parts does it, let's say, which parts form it? First of all, it is the union of two figures. One of the figures is an ellipse. This ellipse is exactly the circle that encloses the spot, but because we look from some angle on it, it actually transforms into the ellipse, because the linear transformation of a circle, the projection of a circle on some other plane, is always an ellipse. So this is union of the ellipse and a segment here, right? So the answer consists of, let's say, two parts. We'll consider two parts. Yeah, this ellipse is touching the circle because because it has to touch, because the original circle, if you look like from above, you'll see the picture that the circle touches the whole planet, and when projecting something somewhere, it still has to touch. So you have the area consisting of this part and this part and this part. Let's join these together and call this the first part, and these together and call this the second part. The first part is actually a circle segment. So if we know these points, it is not hard really to calculate its area. You just need to subtract the area of a sector minus area of triangle. Okay, and this part is actually a segment of an ellipse, and segment of an ellipse is a bit harder to the area of a segment of an ellipse is a bit harder to calculate, but not really hard. If you know everything about this circle, if you know, for example, its let's say its height and its width, then it is possible to calculate the area of a segment by stretching the ellipse back, making it circle, and then calculating the area of this part. So we stretch this ellipse back to the circle. We have like this part transform into this part. So we calculate once again the area of a segment here and multiply it back to the scaling factor. Okay, so what do we have to know here? We have to know the following values. It's good for us to know the height of an ellipse. I mean the height of our projection of view of an ellipse. Its width of an ellipse. What is the width of an ellipse? Width of an ellipse is the width of an ellipse. It's like this. We have to know like h, like w, and coordinates of these points. Let's say the absolute coordinates. So we have also to know these points. P and the Q will be symmetric. Let's say that we have a coordinate picture passing through the center of the picture. So here is the beginning. Okay, how to calculate h and w? This is the easiest part. Actually, W, once again, let me remind you that the picture looks like the following. We have an Earth over here. We have a spot that is over here, and we are looking from like over here. So actually, the width of this spot is exactly the same as if we were looking from the above. So the width is actually the diameter of the spot's enclosing circle. So W equals to the diameter of spot, and the diameter of spot equals to something like, assume that the radius of the sphere is 1, so the diameter of the spot will be like twice the sine of a radial angle of a half of a radial angle of this spot. So this is pretty easy to calculate. Okay, what is H? H is also not really hard to calculate. H is a projection of this segment onto our view plane. This is our view plane, and we are interested in an orthogonal projection in this direction. So the length of this segment is also like length of this segment multiplied by some sine or cosine. So it is diameter of spot multiplied by some sine or cosine. I'm not going to write exact formula, by the sine of this angle. Alpha may be something different in the statement, don't worry. So multiplied by sine of alpha, cosine. Okay, so we know W and H. Knowing P is a bit trickier. How do we get to know P? Let's say that we have a following recipe. We also may know that center of this circle, or this ellipse. The center of this ellipse is a point that is a projection of the center of an enclosing circle of a spot on our view plane. So we may easily calculate it also. We have it over here, and actually what we want to find is a point on the ellipse that is defined by its height and its width, that is shared with the circle, with this large circle. How can we do that? I think you may just want to find this point using, for example, the ternary search. You want to find the point where two functions are the same, with one function being strictly larger than this function. So you may find it using the ternary search, but I think it is possible to find it in constant time. Let me think. We want to find the point of touch of those two circles. What is exactly those point? That point is the point that is the this is exactly our view. Okay, looks like I don't know how to find it more easy. Let me think about that after the editorial. I think it is still possible, but there are lots of ways to find P without that. You know everything you need about the ellipse, you know everything about the circle, so just do whatever you want and find this point for example, the point such that consider the upper half of an ellipse as a function of x, and find the x, find the y, and you are done. Okay, so we know P, and then we calculate everything as we want. There is also a bit tricky case, like the half of the cases look like this, and there are also cases when we look on the planet like this. In this case, the picture will be a bit different. It will be, I think the ellipse will be like about the same, but the spot will take only this part. So instead of calculating the sum of area of this and this, we'll calculate like the difference of area of this and this. Actually, the interesting fact is that if you write a solution that does not use many conditionals, it will most probably it will be working even for the case when we're looking from beneath, from below, because usually it works without like it has all signs being correct inside it, so it just has to work. Okay. Are there any questions about this problem? There were no precision issues. This problem was just about not being afraid of working with a 3D geometry, and I ask you to find the time and to implement it. Yeah.
How do you handle the case when you are looking the sphere from above? Because you don't have to consider that circle, that sphere portion.
From the above.
89 degrees.
Yes, that's a good question. Yeah, this is a case that you have to consider. In this case, you have, let me imagine, so you are looking like this, the ellipse is like this. At some moment it will be, no, I think, wait a second, the picture is always like this. Even if you look at 89 degrees, let's say, if you look on this picture like at 89 degrees, it will be that the ellipse part, wait a second, no. Once again, yeah. So if we look like this, the picture is like this, but starting from some moment, it will be just an ellipse. Yeah, okay, yeah, you're correct. So if we look from here, like without having this part, then you will have only the ellipse, ellipse on the sphere. Wait a second, that's something strange here. So if we look from the horizontal direction, then we have exactly this picture. We start to looking from above, and we get at some moment today is definitely not my day. I don't know. So my laptop has discharged. Was that case really possible in this problem? You asked me. Yeah.
I think that if you look to the sphere
From above.
degrees,
Yeah.
from above just to the North Pole,
Yeah.
you see a disk with a circle in the middle.
Yes.
But if you move a little, for example, 89 degrees,
Yes.
that circle deforms and it's now an ellipse,
Yes.
and you have to determine its area.
Yes. Well, its area is pretty easy to find out. Actually, its area will be exactly the original area of the disk multiplied by the cosine of the angle of projection. But the question is, what is the critical moment between this position and that? I think the critical moment. The critical moment is actually defined by the situation. Yeah, if you start rotating your vector like this, like in the start looking from above. Actually, these 2 points start moving one to each other. At the moment when they get together, will be the moment when the ellipse starts, like it becomes no longer attached to the border of the sphere. I think that's exactly the case when. This is the point starting from which you have to just multiply the area of a disk Yeah, multiply the area of the disk by the cosine of the angle. We actually could have done something similar here. We could have, well, the area of the ellipse is always the original area multiplied by the cosine of the projection angle. But if we did that, it would be hard to find out the area of this part, because we still need to somehow manage to investigate the properties of the ellipse. Well, whatever. Okay, so there are three cases. Looks like there are three cases. The case when the picture looks like this. The case when we look really from above, or even four cases. The picture looks like this. When we look from above, it is just simply the area of the ellipse. When we look from here, it is the difference of a segment and an ellipse. And if we look really from here, actually it will be empty. And I think that this case can be handled exactly like this case, because they are somehow similar. The moment when the ellipse detaches the border is also the moment over here when you stop to see it at all. Stuff like that. Okay. Yeah.
Another question about the precision. Here in the statement says that the relative mean error should not exceed 10 to the minus 8. But you're handling with numbers that may be pretty close to 0.
Yes.
Relative error may be something difficult.
There is only relative error, not absolute or relative.
Yes. Relative.
I think that's a mistake in the statement. I think that they used the standard checker using the test lib, and it was actually absolute or relative. I don't know why did they decide to write the relative. Let me check that. I could check that, but my laptop discharged, so I can't answer this question. I think that they have used the standard checker that checks the absolute or relative error. Good question. Any more questions? Okay, so what was the problem 1 about? The expected value, yeah. So problem 1 was about the expected values. Let's say problem 1 was about the expected values. You had a labyrinth. Several cells of it were blocked. And you had to find the expected value of a minimum distance between the point that is chosen uniformly inside the non-blocked area and the closest wall to it. And the distance was calculated in a metric like the length of a vector xy was the maximum of xy, absolute value of x and y. What is this metric about? It is about actually, like, from here you may get in a unit time to all the points that are over here. So this is the unit circle in this metric. Okay, so the expected value of such a random value, expected value of the answer is the expected value of such of continuous random value. So we should have like some integration somewhere here. Let's imagine the picture like the following. Well, you see that here on the borders, on the walls, the value of, let's denote f of xy, is the minimum time of getting to the wall. On the walls, exactly on the walls, the value of the function will be 0. And actually, for all the remaining points, it will be some piecewise linear function of 2 arguments. Actually, for all points that are, let me see, for all points that are here, it is closer to get here, yeah, of course. So for all points, for example, for the point here, it is closer to get here. For the point here, it is closer to get here. So actually, it is, if you imagine that the function, it grows like out of the board, it will be 0 on the borders, and here it will be some piecewise linear function. I think it will have the form of like, it's hard, let me try to imagine. It goes like over here it is closer to get here, over here the closest is here, so it gets below I think it is like over here, something like the pyramids and so on. So here it is getting below like this, well, whatever. So we have some piecewise linear function. Why is it piecewise linear? Because in a small area that does not, such that all points here are closest to the same like wall, in the small area the distance will always be just an x plus constant or y plus constant or c minus x or c minus y. So okay, also note that this function, this piecewise linear function, it has vertices only in the points that have integral or half of the integral coordinates. Actually, all the interesting points we have are the points with integral or half the integral coordinates. Between those points, all the remaining values of our function may be restored by the linearity. So what we have to do here, actually we have to run like a BFS starting from all the points that belong to the walls, making the distance, the value in them be equal to 0. Then we run a BFS, and for all points that are integral or half the integral, we calculate the distance to the closest wall by using that BFS. After that, we have a function that is a piecewise linear function, and we know its values in all its, let's say, vertices, in all its points that define it, and we may find out the expected value of xy, that is integral over all area over all xy, f of xy dx dy divided by the area of all like empty points. We may calculate it by considering each square of a lattice and just saying that the integral is the sum of, let's say, 8 integrals over such a triangles. And integral over a triangle is what? Actually, integral over the triangle of a linear function that passes through 3 points is always what? I think it is something like the value, if you have a triangle, then the integral here will be like, if the value here is a, the value here is b, and the value here is c, it will be always 1/2 of 1/3 of a plus b plus c. Yeah, I think like that. Because the function is linear, so yeah, the integral of the area below the triangle in a space is denoted by this formula. This is an area factor, the scale factor, because the area of the bottom is 1/2, and this is the average height of these 3 points. So yeah, this is the whole solution. You have to write a BFS here. You have to carefully integrate over all the triangles. It works in a linear time, so that it is. Are there any more questions? Questions? I don't remember. Did anyone solve this problem during the contest? Yeah? Did you do about the same? Well, okay. And what time do we have? I think the time is almost gone. Wow. So that was the first problem. Let's discuss the fourth problem. And here I have failed you again. I forgot about that problem. I didn't manage to think about it yesterday. So I don't I don't remember my solution 3 years ago. I remember that there was some combinatorics. So I don't almost have anything to tell you. I can tell some ideas. The first idea: if you ever get such a problem on a contest that runs in online, that is not ACM, ICPC, then you may do the thing that the team who submitted this problem during the contest did. The team that actually, I think they have written the stupid solution to find several few values of the function, like several first values, and then just put those values into the OEES, the online library of all the sequences, and then just to put the values inside your code. If it was an online contest, it would be a really good solution, like if it is not prohibited by the rules, of course. But if you are like in ACM ICPC style conditions, then you have no option to do that, and you have to think about the solution. Like, it is okay, it may help you to have several few values to make sure that your solution is correct, but it's not really a way to solve the problem. So the idea in that problem was the following: you had to calculate the number of equivalence classes of the graphs that look like they consist of cycles with trees attached. This is a really common kind of graph. The graph that corresponds to all edges of form from V to f of V, where f is the unary operator that we have. So the graph looks like this always. And you have to calculate the number of isomorphic classes of such graphs. Number of isomorphic something may be calculated using the Burnside's theorem, or lemma of the Burnside, and this was the case. The lemma of Burnside states that the number of equivalence classes of some objects under the action of some group of permutations, under the action of some group, is actually 1 divided by the number of possible elements in the group, by the number of possible actions. We have like n factorial actions of interchanging of vertices, multiplied by the sum of the number of fixed elements, the elements that are not affected by the permutation sigma over all sigmas, the permutation on n elements. So this is the Burnside's lemma, and in this problem you had to somehow calculate this thing by iterating over all possible set of cycle lengths inside the sigma. You see, when n is smaller or equal than 50, then the number of partitions of n into the sum of several terms is no more than I think 10 to 6, as I remember. And you had to somehow iterate over all possible, what is the partition of n? N is like the expression of n of form L1 plus L2 plus so on plus Lk, where L1 to Lk are unordered. And actually to each such partition, it corresponds a unique permutation up to the up to the renaming of the elements. So if the single permutation of that kind. And here you had to somehow fixing the profile of such form, you had calculated the f of sigma, but I didn't come up with an idea how to do that while walking over here. So I am not sure that I am going to do that like in 2 minutes using the board. So I don't have much to talk about that problem. I will also try to write down and send you a solution. So, okay. I think that's all for the editorial. We can make a break. If you want to, you can ask the questions about something that we had here. Yeah.
I think I just came up with a formula for the problem.
And we have not the length of the path, but the like another function that is of form sum of something else. So it is not really simple to transform one to another, because in denominator you have not really a number of edges in your path, but something more complicated, a number of watchmen, of guards across the path.
That the number of watchmen, the numerator?
It is a numerator. No, in the statement it is a numerator. Okay, the statement asks about minimizing the sum of guards of E divided by the sum of let's say area, oriented triangle area of E, right? You first of all transpose it. Well, I don't know if you have any way to convert it to sum of W of E divided by the length. I don't know how to transform this to this. Do you have any way to do that?
Let me just convert this to maximize some infinity minus this.
Some infinity minus this?
Yes, we take every number of soldiers, right, and take like some big number, subtract it, and now it's the real the new value.
I think just putting infinity in a numerator does not work, because it is changing the order of these values. I mean, those who will have the smaller area will be much better, because you have actually added like infinity divided by the area plus the old value. You have added it, and those who have smaller s will be just better than the other. So I think this doesn't work.
In problem 10, we are considering what's the denominator in problem 10? What's the
Denominator? The area of coverage of the polygon covers.
I thought it was the length.
No, that was not there.
Sorry. That's what's missing. Thank you.
Okay.
Do you think the solution can be adapted? Is this something like that?
I don't think so. I think
different.
Solution is exponential by its nature, because
Sorry?
I think the solution should be exponential. You are trying to come up with the polynomial solution, and I think it can only be calculated using the exponential time.
Makes sense.
Because I think so.
Hard.
Okay. I think we're going to spend a few more minutes here.
Don't worry.
Okay.
Before you finish, we are going to take the group picture today. So at this day, so do not let them go away.
Okay.
We should have a special prize.
Okay. So, okay. I think I'm going to just spend like 20 or 30 minutes on talking about the dynamic programming we started yesterday and we didn't manage to finish because we don't have much time enough. Well, all our lectures during this week were kind of really short because the editorial took much time, and I hope that with Mikhail you will get like more time to discuss some topics. I think he's going to teach you some graphs and maybe, I don't know, maybe some strings also. So I'll just finish the dynamic programming part. Well, the thing that we didn't manage to get done was the two kinds of optimizations, the divide and conquer optimization and the Knuth optimization. The Knuth optimization is really a great thing. It is a very simple but still very powerful way to just reduce the magnitude of the complexity by by n or by n squared sometimes. So it works pretty like this. I think most of you should have the yesterday's paper with you, so you can just look on it. The problem, for those who doesn't have it, the problem looks like this. Suppose that you have a set of keys, let's say x1, not keys, let's say weights, w1, w2, and so on, wn. And what you want to do is to put them into a binary tree, let's say wi, such that binary tree contains exactly all the elements you have in exactly this order, like w1, w2, w3, w4, w5, and so on, up to wn. And you have to minimize the following value. The value of sum of wi multiplied by the depth of I. Depth for the root is 0, or let's say for the root it's 1, for the second level vertices is 2, and so on. What's the idea behind this problem? Actually, if you say that weights are the probabilities of access to some keys in a data structure, then what you minimize here is the expected value of getting an access time to an element. For example, you know that you are going to store I don't know, people in a database according to their telephone number, and you know that some people are being called more often than the others. You have to put all of them into a binary search tree such that the expected time of an access is as small as possible. You can just build a perfect binary tree, but it will not be really how to say, really the most efficient way, because you access some guys more often than the other ones, so it is more convenient to put them more close to the root. This is somehow similar to Huffman's encoding, but for a different problem. So how to find out which the binary tree suits the most for the given set of weights? This problem also is called the optimal binary tree problem. It was considered by many authors. Well, the dynamic programming solution was found really almost immediately, but it took 20 or 30 years to notice that it may be optimized by one extra dimension. So what is the dynamic programming solution? The dynamic programming solution is like the segments dynamic programming over the segments, where you consider the segment LR in your sequence, and the value is what is the minimum possible sum of the access times of the weights multiplied by the depths if we consider only the vertices from L to R and put only them into the binary tree. So DLR is actually the answer for WL up to WR. What's the dynamic programming solution? What's the dynamic programming formula for such a function? Well, first of all, the base would be for empty segments. It is 0 because the sum of weights multiplied by depths in an empty tree is 0. And for a non-empty tree, you first choose some of the vertices to be a root. You decide that some vertex, let's say some vertex I, some number I will be in the root, and then everything that is to the left goes to the left subtree, and everything that is to the right goes to the right subtree. And the weight of such of such scheme will be wi as the way of the root plus the answer from L to I minus 1 plus the answer from I plus 1 to R, but those answers, they do not consider the fact that the depths are calculated not from this place, but from this. So we actually have to add the sum of weights over here plus the sum of weights over here, and I will write it simply as a sum of Wi, of Wj between all among all the numbers that we have in this range, plus the answer for the left part plus the answer for the right part. Notice that this is actually a constant, so I may write it outside the brackets. Also, this constant is actually a sum a sum on the segment of all weights, so it may be expressed using the partial sums. So I will just write it like S of R minus S of L minus 1. Okay, that's the dynamic programming formula that works currently if in O of n cubic. We want to do it faster. Donald Knott was the first who noticed the following fact. Denote as the optimum opt I of LR the optimum number to be chosen as a root. So let's say it's the optimum I. Over here. He noticed the following fact. What happens when you move one of these bounds to the left or to the right? What can we say about opt I of LR and opt I of LR plus 1? Well, it's pretty natural that if you have set of vertices, some optimum binary tree for them, and you have the more wide range of numbers, and you have a binary tree for all of them, that the root for the more wider range will be to the right, in respect to the root for the shorter range. So it is true actually that opt I of L and R is smaller or equal to the opt I of L and R plus 1. How do we prove that? Well, we prove it. Okay, I'm not going to give you a formal proof. That's not my best part, as you have already understood. It can be proven like this. You just look on all numbers from WL to WR. On new number WR plus 1, consider the path from the root I, opt I, to R, the right path. Consider the same path for the situation when you have WL, WR, WR plus 1, and the right path goes to the R plus 1. Consider the opt I of L R plus 1. Suppose that it is smaller than opt I of LR. So you have the following situation. Among these paths, the vertices, like this vertex, it is to the right of this vertex, but this vertex is to the left of this vertex. There is some moment at which the transition, like two edges crosses, if we draw both of them on the same picture, and exactly at that moment you get a contradiction. So, okay, suppose that we know this fact, and due to the symmetry we also know the following fact, that opt I of LR is smaller or equal than this. It is larger or equal to opt I of L R minus 1. On the other hand, it is larger or equal to, let's say, it is smaller or equal to opt I L minus 1 R, and it is larger or equal than opt I of L plus 1 R. So we have the four relations. If we draw them schematically on a picture, it would look like the following. It will look like the following. Here you have the table of all the values of a dynamic programming. This is L, this is R. L is smaller than equal to R. It means that we are interested only in this part of our table. In the part that is below upper part above the line L equals to R. So we actually have all the values here. And what do we have? If we have value over here, value LR, then it is smaller or equal than LR plus 1. It is larger or equal than LR minus 1. It is L minus 1R. L minus 1R is larger or equal than LR. It means that this is larger than or equal than this, and this, and so on. So it looks like the following. And this gives us, sorry, it doesn't look like the following. It looks like, yeah, if with fixed L, if you start increasing R, it increases, and with fixed R, with larger L, it is still, I think the signs should be like this. Opt L minus 1 R should be larger than opt L R. L minus 1 R. Here I am wrong. L minus 1 R is like this, and this one is like this. Yeah. So the picture is like the following, and it allows us to do a pretty beautiful optimization. You see, let's calculate the optimal values, the dynamic programming, not in the direction like this or this. Let's calculate it in diagonal direction. So starting from the ones that are on this diagonal, then this, and so on. Yeah. Did everyone understand this statement? Are there any questions? It looks like this on the picture, so we will now use it. Okay, let's try to calculate our dp in order of increasing R minus L. It's actually the order of increasing length of a segment. So what does this help us? How does this help us? Actually, when we calculate DLR, we may write down the following formula. It is the minimum over all I, but not between L and R, but between optimum of L R minus 1 and optimum of L plus 1 R. Of the same stuff, of the DL I minus 1 plus DI plus 1 R plus SR minus SL minus 1. So we just put more tight bounds over here. Here we had L smaller or equal than I smaller or equal than R, and here we have more tight bounds. We know that opt L and opt we know the optimum positions for the layer that is below us. Okay. What does that mean? Actually, that means that opt LR lies between these two guys. Opt, like, of this point lies between these two. Also, this one lies between these two. So if we draw this layer, previous layer, and current layer, then in current layer, the sum of lengths of all those ranges will be exactly, it will be linear, because all those ranges, opt LR minus 1 and L plus 1 R, they are all actually forming the set of lines between the 1 and n. These are just some points, and calculating the ith, some certain dp here requires to iterate over the segment here. In total, all the sum of lengths of all those segments is linear. It means that the whole running time will be O of n squared. So, did everyone get the idea? Yeah.
Why E not is equal optimal LR?
Why does E fits inside LR or what?
Because E not equal optimal LR. The element from L.
We do not. You ask why not simply put I equal to optimal LR? We do not know it yet. We do not know optimum LR from anything. We know only the. Well, we have calculated the values of dp for all LR such that R minus L smaller or equal to D minus 1 for some D. Now we are going to calculate for R minus L equal to D. You see, we calculate the value of opts for all points here, and we want to calculate it here. We do not have opt LR right now. We want to find it out. In order to find it out, we just calculate DLR using that formula, and the point that yields us the best I, it will be actually the opt of LR. Any questions? So this is, yeah.
The base case is written different.
Let me check. What is different?
The base case of the DP should be 0. It's 0, right?
L minus 1, yeah, it should be 0 first, yeah. There are, like, I think many mistakes there, but I'm fixing everything and putting the new version on the side. So, thank you. Okay, the other should be 0, yeah. So this was the Knuth's optimization. It is pretty popular nowadays. Let's also have a brief talk about the divide and conquer optimization. I haven't seen a problem that was only possible to be solved only by a divide and conquer optimization, but still it is really an interesting way of optimization, even from the theoretical point of view, and maybe at some moment there appears a problem that requires exactly the DNC optimization, so I suggest you to know it also. What is DNC optimization? It's about the following. Suppose, yeah, one more fact. If you had two, like in this problem, the arguments L and R, they are kind of symmetric to each other. They all belong to the range from 1 to n. And that's why the transition from n cubed to n squared looks natural. But if you had a dp from two different parameters k and l, let's say n varies up to 10 to, let's say, 5th, and k varies up to 10 squared, up to 100, then it is not, and it holds the similar kind of relations. In order to be able to use the Knuth's optimization, you have to have something like some inequalities of the following form. Some value at the point should be smaller or equal than the value of one adjacent by horizontally in horizontal direction and greater or equal in a vertical direction in some of two directions. So even if you have such for the dp that is like not a square dp, not the ranges are of different magnitude, that means that the overall running time will be still, if you sum up all those, like for a diagonal it works like in n, in time linear by n. Then if you have such a picture, it will work not in O of nk, it will work actually in n plus k multiplied by n. So it is actually O of n squared. Actually, the Knuth optimization works in it does not allow you to optimize the dp that has parameters of different kinds. Be careful of that. And divide and conquer optimization, it allows you. Actually, suppose that you have a dp like, let's say, dp that satisfies the following criteria. Opt kn is let's start from an example. The example is what is written in your paper is the following. We have a list of numbers x1 up to xn, and we have to divide it into the parts such that if we sum up for all the parts f of the total weight of the part, sum of f of sum of weights, let's denote it as si. Si is the sum of weights of the ith part. We have to divide it into exactly k parts such that sum of functions of that parts is as small as possible when f of x equals to x logarithm x. Here I could have put the x squared, and in fact I could have put any convex function, but let's consider that case. It is actually equal to minimizing the product of factorials of all those numbers, let's say. So how to do that? First of all, the dynamic programming solution would be dkn equals to the minimum possible value of that stuff that we can get, dk, let's say dij, minimum possible value of that stuff if we have split the prefix of length j into I parts. Okay, what's the value of dij? First of all, the value of d0, 0 equals to 0. That's the only base value, and dij equals to the minimum over all, I don't know, z between smaller than j, larger or equal than 0, of di minus 1, di minus 1 z plus f of the sum of all elements between the z plus first and the jth one. And let's say that this is the length then from z plus first to jth one. Then here we'll have something like sj minus s z, where s are partial sums. Okay, we want to optimize such a dynamic programming. It may be shown that if you have a relation, if you have a convex function, then the optimal z of ij is larger or equal than the optimal z of I and j minus 1. I'm not sure how to prove that easily. I know only one proof that requires the knowledge of a so-called Karamatas inequality. That's the inequality for the sum of the convex functions, sum of values of convex functions. But Well, I don't know, maybe there is an elementary proof of that. If there exists, I'd be glad to hear about that. I have written the exact name of the theorem in the statement. You may just read it and try to use it here, like using the induction. I can tell to those of you who are interested how exactly to do that. So if we have such a condition, here it holds, then let's try to figure out how to calculate the dp. The dp, in this case, in this form, it works in O of kn squared, and we will optimize it to O of kn log n. So how will we do that? Here we have our table of dp. Here we have n, here we have k. The value of ij, it depends on the value of I minus 1z, like the sum, it is equal to sum of the value, some value here, plus the function that depends on those 2 points, or plus some convex function on z and j. How can we use it? Actually, let's do the following. Suppose we have already calculated everything over here. We will not be needed the values of opt z for the lower layers. We're just going to calculate it for the new layer, for this layer, and we will be storing. We will not even be storing them. We may just pass them to recursion, whatever. So we'll do the following thing. Calculate the value of the I and n1/2 of n, this value, calculate it using the linear formula. You see, we may actually calculate the values of this dp in arbitrary order because they depend only on values of dp of the previous layer. They do not depend one on each other. So we may start to calculate it like from left to right or from right to left. Actually, the best order to calculate them here will be not the order from left to right or from right to left. It will be the order of divide and conquer, the order of like layer traversal of segment tree. You see, we'll start with calculating here, then we'll calculate here and here, then we'll calculate here, 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 and here, and so on. First of all, start with calculating the value here using the linear time algorithm, using this formula. This formula requires the whole path with the pointer z between here and here. So this value will be calculated in O of n. Okay. What do we know now? Now we know that for this value, the optimal pointer is somewhere here. What does that mean? We know the opt z of I and j, of I and n divided by 2. Okay, let's make a recursive call. Let's make a procedure that gets a range and that calculates all the values of dp and all the opt z's inside that range. How does it do? How does it works? It calculates the value in the middle and then makes 2 recursive calls. For example, let's calculate the value of dp over here. What do we know about the value of dp over here? Well, that's bad picture. Let's calculate the value of dp over here. We know that the optimal value of z for this particular point, it is not only somewhere to the left of this point, but it is also not less than opt z of I n divided by 2, because n divided by 2 is to the left of it. It means that for this point we'll have to traverse only this part of our of array of the previous previous values of dp. We'll need only to look on these values, and we'll find out some optimal pointer over here. Okay, let's calculate the value over here. It still relies only something over here. Well, let's say that pointer here has pointed like more to the left. Then it means that value here are, we are interested only in calculating like these values. Let's tell that more carefully. If we have a procedure that calculates value of dp for all elements between L and R on the layer of I, we may do the following. We may calculate, we first start with calculating the middle of L and R. We calculate d of I and M using this following formula. We calculate it using this formula, but the z we will consider only in the range of opt z I L minus 1 to opt z I R plus 1. It is invariant of our procedure, invariant, that opt z I L minus 1 and opt z I R plus 1 are calculated by this moment. So calculate DIM using this formula and calculate it using this formula, and then let opt z of IM be equal to the optimal z that may be found, I mean optimal z in this case, and then make a two recursive calls, go of L M minus 1 and go of M plus 1 Ri. Notice that if we had this invariant fulfilled, then by this moment it will also be fulfilled. In both points L minus 1 and M, the opt z is known, and in both points M and R plus 1, it is known. How can we call this procedure at the beginning? At the beginning, we just let the opt z of 0 and of n plus 1 be equal to respectively 0 and n plus 1. This is some kind of barrier values. And just run this procedure. Why does it work fast? How many operations? Let's say that we tell that this recursive procedure, it makes several layers of recursive calls. The maximum possible depth that you can get during these recursive calls is log n, because each time the length of the segment LR divides by 2. So what's the maximum possible depth? The maximum possible depth of recursion is log n, and actually I claim that for each layer of recursion, for each layer, the total running time will be O of n. Why? Because let's look more carefully on this picture. On the first layer of recursion, we calculate opt z of this point in a linear time. This is the first level point, first layer point. On the second level, we calculate values of these 2 points. They are second layer points in total in linear time, because iterating for this and for this, they both iterate from the left to the opt of this point and from this point to the end. Let's say that we allow iterating to the end. Okay, the third level calls. We know now these pointers. Here are the third level calls. Third level. This one iterates between these two, this one iterates between these two, this one iterates between these two, and this one iterates between these two. It means that the third layer calls in total also work in O of n, and so on. So the running time for one value of I will be n log n, and the total running time will be O of k n log n. This is how the divide and conquer optimization works. It requires it usually works in problems like divide something into several parts such that, and it requires for you only the monotonicity by one of the pointer by one argument. So it's kind of a cool optimization. But it requires you to be able to calculate values of dp for the next layer by I in any order, to be able to calculate it in any order, not in some specific order. So the value of dp should not depend on the values from the same layer. Okay. I think that's all. So, first thing to tell, we are right now not leaving. We are going to take a group photo, so just not run away when we finish. So thank you for attending my classes. That was really fun. I hope you learned something new, except that I do not prepare for the editorials well. And thank you. I hope to see some of you maybe on some competitions in the future. Thank you.
I think you have already thanked Maxim for this.
Yeah,
I would like to personally thank him for being with us this week. And I have a few announcements for you. Did announce the Facebook.